Le Chatelier's principle. Quoting Le Chatelier, if a system at equilibrium is disturbed by a change in temperature, change in pressure, or change in concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. This principle states that if a system's equilibrium is disturbed, the system will react so as to reduce the impact of that disturbance. With concentrations of reactants or products, the interpretation of this is pretty clear. If the amount of reactants is increased, the equilibrium will shift, using the additional reactants to produce more products. This reduces the amount of the added reactants, thus reducing their addition. If the amount of products, so first we talked about reactants, now we're going to talk about products, if that's increased, the equilibrium will shift, using the additional products to produce more reactants. This will then reduce the amount of the added products, reducing their addition. Changing the concentrations of either reactants or products disturbs a system. It creates a stress. In response to that stress, the system will shift to a new equilibrium position. So let's first look at what happens when we increase the concentration of either reactant. That causes the reaction to consume some of those added reactants, reducing the amount of their increase while creating more products. So what we have here, we're increasing the amount of A, one of the reactants. That's going to shift the equilibrium to the right to make more products. So you can see the arrow here. There's more reaction going to the right than left. Same thing happens if we were to shift B. More of the reaction is going this way to make more products. Now let's decrease the concentration of either reactant. Let's first decrease A, and hopefully you can see how the arrow is bigger going from right to left. We're shifting the equilibrium. That will tend to replace the reactants that we're consuming. And of course, the same thing happens if we decrease B. The reaction shifts, so more of it is going from right to left than from left to right. The same principle holds for a change in the product concentrations. The system will react so as to reduce the extent of the change. So by increasing the concentration of either product, that will cause the reaction to consume some of those added products, reducing the amount of their increase while creating more reactants. So if you increase either C or D here, those are the products, the reaction shifts, so more of it is going from right to left, okay, from products to reactants, then from reactants to products. Now, what if we decrease the concentration of either product? Well, that will cause the reaction to produce more products, replacing some of those which were lost while consuming some reactants. So you can see more of the reaction now is going from reactants to products. What if we change the temperature? Think of the heat absorbed or released from a reaction as a reactant or product. Then just apply Le Chatelier's principle to heat as you would for any other reactant or product. For an exothermic reaction, consider heat as a product of the reaction. Then consider an increase of temperature as an increase of products, which will drive the reaction towards reactants. How about an endothermic reaction? Well, this time consider heat as the reactant. Then an increase of temperature is an increase of reactants, which will drive the reaction towards products. So here's what we mean by considering Q as a product. We'll start with an exothermic reaction. It releases heat to its surroundings. So we're going to rewrite the equation, which started off just like this with the reactants and products. We're going to put Q on the right side. Now we're going to increase the temperature. That's the same as adding more product, with treating Q as a product. So that will drive the reaction back towards the reactants. Just like if we increased either C or D, the reaction would go right to left. If we decrease the temperature, that's the same as reducing a product. So the reaction will proceed towards the products, like shown right here. This is very similar to Lenz's law in physics. If you've had physics already, you might see the similarity. Let's now look at an endothermic reaction. Heat is being absorbed from the surroundings. So we're going to write Q as a reactant. So here's our basic equation before we do anything to the heat. Now let's increase the temperature. That's the same as adding more reactant, Q. So this goes up, which means the reaction shifts towards the products, left to right, just like if we increased either the concentration of A or B reactant. If we decrease the temperature, that's the same as reducing a reactant, so the reaction will proceed this way towards the reactions. Applying the principle to a change of pressure is a little less obvious since pressure is not a reactant or a product. However, a reaction in a sealed container will result in a change of pressure if there are a different number of moles of gas on the products or reactant side. More moles of gas, more pressure. Then the principle would indicate that an external change in pressure will result in the reaction proceeding so as to reduce the extent of that change. For example, in this reaction, the reactant side has 4 moles of gas. Okay, here's 1 of nitrogen, here's 3 of hydrogen, 1 plus 3, 4. And on the right side, there are 2 moles. As the reaction proceeds from the reactant side to the product side, the result will be a decrease in pressure. If the external pressure on the system increases, the reaction will move towards the product side to reduce the extent of that external change. A reduction in pressure will move the reaction towards the reactants that way. Let's draw it with the correct arrows here now. We've increased the pressure that the reaction is taking place, so the reaction will proceed towards the products to reduce the pressure. Now, if the external pressure is decreased, then the reaction will proceed towards the reactants to increase the pressure. This effect only occurs because the number of moles of gas is different on the two sides of the equation. If they were equal, a change in pressure would not shift the reaction in either direction. Let's look at a volume change now. A change in the volume of the container in which a reaction is proceeding will result in a change in pressure. You have a decrease in volume, you've increased the pressure. Increase in volume, decrease the pressure. In those situations, first determine whether the pressure has increased or decreased. Then use what we just learned about how to apply Le Chatelier's principle to a change in pressure to solve the problem. Changing the pressure of a reaction by changing the volume disturbs a system. It creates a stress. If there are different numbers of moles of gas on the right and left sides of the equation, the reaction will proceed to change the number of moles of gas to reduce the extent of the external change. In response to the stress, the system will shift to a new equilibrium position. In this case, there are 2 moles of gas reactants and 3 moles of products. Here's the product, here's the reactants, same for both of them. So in the first case, we'll increase the volume, which means the pressure goes down. Therefore, the reaction will shift to the right to produce more product. If the volume goes down, then the pressure goes up. In that case, you shift over to the products. Ammonia is produced for agricultural fertilizer and other industrial uses via the Haber process, the synthesis of ammonia from hydrogen and nitrogen, one of the more important chemical reactions in modern society. We will use this process to study Le Chatelier's principle. So here you have nitrogen combining with hydrogen, forming ammonia. Our equilibrium constant is 6.0 times 10 to the minus 2 at 25 degrees Celsius. That means the reaction favors the reactants, not the products. What can be done to make more products? The temperature can be changed because the only way to change K, the equilibrium constant, is to change the temperature. Now this is an exothermic reaction. In order to shift K towards the product, the temperature would have to be lowered. Lowering the temperature will decrease the reaction rate, which is not acceptable in industry. Okay, it works, but it's not very cost effective. Another possible solution is to increase the concentration of the reactants. By adding more reactant, the reaction shifts towards products. Now the equilibrium position will be reestablished and more product will be produced. So here's our concentration here. And what do we want? We want more product, which is the ammonia. And you can see how it's going up once the nitrogen was added. That shifted the equation to the right, so more ammonia gets produced, which is kind of the goal. What you also can do, and this is what industry does, is remove the product as it's formed. By removing ammonia periodically and continually adding more reactants, the reaction forms even more products. It keeps shifting over to products. So here's a little valve that's open, and that takes the ammonia out. And then we have a catalyst here. That, of course, does not change the equilibrium constant, but it does speed up the reaction, also a positive for industry. Now, sometimes changing the temperature is the best way to shift a reaction in one direction or the other. Not for the Haber process, but let's look at this one. Let's increase the temperature of this system. We have a delta H is 88 kilojoules, and it is endothermic. Since the reaction is endothermic, view the energy as a reactant, just like we did earlier with Q. The system should accept, which means take in the thermal energy supply to favor the endothermic reaction. And then the equilibrium will shift to the right, the forward reaction, to produce more product. When the temperature of this reaction is changed, there is a dramatic change in the appearance. We have cobalt hexaqua ion, which is a pink solution, and then we have an anion, cobalt chloride, which is a blue solution. And this chemical is also used in fish tanks, because look what it's doing. It's combining with chlorine in the water and turning it into this ion. Chlorine's not good for fish, so it helps get rid of that. Delta H is positive here. And let's see, what else do we have? Many ions containing transition metals produce colored solutions. And that's what we just said here. We have a pink solution here and a blue one here. At high temperature, the blue species here is favored. So you have 100 degrees Celsius here, and the solution is blue. At low temperature, the pink species is favored, and you can see that. So please click here for a nice animation. And here's an interesting application of this principle. The reaction that occurs in a car engine is an exothermic process. Right? Gasoline plus oxygen yields CO2 plus water plus heat. Cooling the engine will shift the reaction to the right, ensuring full conversion of the gasoline to energy and its waste products.